So this is kind of a hard talk to give because most, if not all of you, have probably already heard about the result. So I'm going to go fairly quickly through one of the variations, but not go into details about things you probably heard about, and spend a little more of the time talking about sort of the ramifications and the context of Spectre. I'm Paul Kocher. I also wanted to highlight Jan Horn. He actually reported this issue first to Intel, but didn't want to be first in the paper and isn't here presenting. But if anybody sort of should be listed first, it probably ought to be him. So if we sort of look back in sort of the history of making computers fast, there were some early years where it was actually really easy. You'd basically crank your clock rate up, and you would end up getting your computer to run faster and faster, and actually everything kind of got faster at the same sort of proportion. So your worst case performance and your best case performance, they were all gaining in performance. But about 2004 or so, maybe a little after, we pretty much came to the wall when it came to clock rates, somewhere in that 3.5 to 5 gigahertz range, and maybe we can squeeze a little bit past that, but that's about where things max out. And another sort of fundamental problem that we've run into is around memory speeds. Latencies just haven't gotten substantially better. Again, they're incremental improvements, but nothing transformative. So if you look at what's been going on in performance gains in the last couple of decades, a lot of the focus has been on ways of making things run faster in the average case. And this means things like caches, it means techniques like speculative execution, it means things like finding creative ways to compress your memory so that you use less resources or less time to do something useful. So when I sort of think about this from a security perspective, it basically means that when I look at things, this entire area of research around doing computer architecture has essentially become the world of creating brand new side channel attacks. And almost any optimization that you can think of that makes your best case run a little faster, leaves the worst case the same, leaves some kind of side channel in between. So in this talk, I'm going to focus on speculative execution, which is one of these performance increasing techniques. And there are others as well, like using pipelining and such. But the idea of speculation is super simple. It's been known for decades. And it's basically a way of taking hardware, which works in parallel, and using it to efficiently or quickly run a program which is organized as a series of linear steps, the way that most programmers think. So you've got this series of instructions. You don't necessarily know, given a whole bunch of instructions, which ones will interact with each other or exactly how it's all going to work out. But you can start or try to start work on something even before you're certain about whether you're going to need the end result. And if you guess right, you'll go faster. If you guess wrong, you'll be back where you started. So speculation, we're going to start a likely task early and then clean up our errors. So if I have a very simple piece of code, like if x equals 1, then I'll do one thing. Otherwise, I'll do something else. If the value of x is not in the cache, I'm going to sit for a couple of hundred clock cycles if I'm the processor waiting for this value to come in from DRAM. Because DRAM, as I said before, is really, really slow compared to processors. So we've got this long delay, and the naive thing to do would be just to sit there if you're the processor and wait for x to arrive. The optimized thing to do is to basically keep a copy of all of my registers at this point where I'm waiting for x, but proceed using a branch predictor in whatever path the branch predictor thinks is most likely. And branch predictors work pretty well. They're sort of well beyond 90% correct in their predictions. So it will predict, for example, that this statement will be true. I can then start work on ABC before I know for sure if it's true. Eventually, the memory responds. I get my value. I can check to see whether I guessed correctly. If I guess correctly, I win on performance. If I guess wrong, I basically go back to where and execute correctly, but there's not really any performance cost in doing that. So this is kind of a guess right and you win, guess wrong and there's no cost from a performance perspective. A parallel thing that I'm going to talk about briefly is fault attacks. So there have been a number of papers here, one by Bonet, D'Amelio, Lipton from quite a while ago, as well as just a lot of practical work. Like if you look at what pay TV hackers do to break the security systems in the cards that are used to protect satellite services or video game hackers, they are very adept at basically taking a correct program, inducing the processor to make an error at some usually carefully timed location during the execution, resulting in a different programming executing. So common thing that you'll get is you'll induce a glitch and an instruction will effectively work like a no-op, but there are other things that a glitch can do as well. So as an adversary, by choosing where to put these glitches, I can basically rewrite the program that was originally correct and secure into a different program which contains errors. And I've spent an embarrassingly large amount of time in labs basically torturing microprocessors to make them make mistakes. And what you pretty quickly learn when you've done this for a while is if you can come up with really any kind of an error that will change some instruction by choosing when you induce these errors and how you induce them, you can turn any program into something that's exploitable. So there may be some crazy exception where you can't do that, but I have yet to see a processor where I could glitch the thing and break it. So when Mike Hamburg, I don't know if he's here, but he's a researcher at Cryptography Research, asked me the question about whether speculative execution was an okay thing to do in processors. As somebody who's done glitch attacks, this kind of made my stomach feel a little something or other in it. Because basically, this is like the CPU has its own fault attack hardware built into it. I don't need to go and take an analog thing to monkey with the clock line. I don't have to do any of that stuff. It's already there. And there's a little nuance in that it's going to try to delete the errors, but as somebody who's worked on side channel attacks and even done attacks where you combine a glitch and then you measure the power consumption of the thing after the glitch to get some information that you wouldn't get directly from the normal power consumption, the idea that all this stuff was there and I can just use any of the covert channels that have been known about, again, since well before I was born, to exfiltrate information from this incorrect execution into some place where I can do something with it, seemed almost too good to be true if I was wearing an attack hat, but as I think we all know now, that's exactly what's going on in our performance-optimized microprocessors. So I'm going to quickly run through the variant one of the attack. I'm not going to go through the others just because of time here. So the basic context for a typical sort of variant one Spectre attack is that there's some code that's going to run in a trusted context where an adversary maybe can control some input into it. So in this example here, I've got a little snippet of code where there's a index coming in that the adversary might be able to supply. There's a bounds check at the beginning where it's going to be compared against a size limit. We're assuming x is unsigned. And under just sort of normal in-order execution, this second line of my piece of code that computes y is never going to be executed if x is out of bounds. The adversary in this case, we're also going to assume has configured the cache into a particular set of states. This is not necessarily the only way to make it work, but it makes it easy to understand. So we're going to assume here that the size of the array is a variable in memory, which is not in the cache. We'll also assume that the array 2 is completely not in the cache, but there's some secret sitting in memory out of bounds from array 1, which is in the cache that the adversary would like to find. So the other thing that the adversary wants to do is to train the branch predictor so that it will assume that the if statement is true. So call it a couple times with in-bounds values of x. Not a big deal. So what happens when we call this now as the adversary and we provide a value of x which is way out of bounds, billions, whatever we want. Just basically we're going to supply the difference from the start of array 1 base to the thing that we would like to read out of memory. So we're going to do an out-of-bounds read here, which is not supposed to be allowed because of our if statement. The processor then comes along and it wants to check whether we're in bounds. So it tries to load array 1 size from memory, but that's going to take a long time. It's going to take a couple hundred clock cycles. We're just going to be sitting here if we have an in-order processor, but all of our fast processors now do speculative execution. So they basically just blast on through that if statement as though it were just kind of a casual thing, doesn't matter. Probably doesn't matter for security, right? We'll just keep on going. We'll predict that this if statement is going to be true because it was last time. We're going to then read from array 1 base plus x with our out of bounds x. So we're now doing an out of bounds memory read. Now as a security person, this is the point where I kind of would argue that we are having a security violation. This should not occur. But this is exactly what the processor will do. And in fact, it will then go read the secret byte that we are trying to leak as the adversary. It will then use that as an index to multiply after multiplying by 512 as an index into array 2. The processor will then load that value from memory or start loading that value from memory. It will actually get put into the cache as well. And eventually, after a whole bunch of this goes on, hundreds of instructions execute perhaps, The processor will realize that it made a mistake, that the if statement actually was false, and it will rewind all of the register contents back to where they were before and proceed as though the if wasn't true. Much later, however, when the adversary gets control of the processor again, we can go back and we can simply time how long it takes to read each element out of array 2. And one of them is going to read fast, and it's the one that identifies the secret byte that we were trying to read. There are lots and lots and lots of variations to this kind of a theme, though. You can, for example, here, the way that the leak occurs, it's the change in the cache. But if the processor doesn't actually change the cache while it's running speculatively, the timing of other speculative things can adjust the time of when something else than I can observe occur. If there's any kind of a covert channel between the speculative world and the adversary's world, that gives you what you need to make the attack work. And so if you kind of think about what the sort of world of variations here looks like, there are a whole bunch of different speculation scenarios that go on inside processors. I continue to be discovering these as I read the papers that have been coming out. I'm not a microprocessor guru. In fact, the first exploit code for this I wrote on a piece of paper while sitting in a conference session, just thinking, okay, well, this should work if this thing does what speculative execution says, and surely they know better, but no, never mind. So the first step then is you've got a speculation scenario. There's then some kind of a probably safe computation that becomes unsafe when it's run with these errors. That is a second part of the attack. There's a process then of inducing the speculation with the desired error. And it turns out there are lots of ways that, as an adversary, you can mistrain processors. You can change the ways that caches are configured. You can make a lot of these optimizations work in ways that are, again, beneficial. They're beneficial for performance in the average case, but not necessarily good for security in the pathological cases that an adversary might introduce. We then have some side channel. There are lots and lots of side channels in our modern chips, and then some kind of detection and analysis process. So there have already been a whole bunch of related results, and there will be, I think, some at this conference, some at other conferences, and they're going to be more. I'm aware of results that are still under embargo. I'm aware of more things coming, and I'm sure there are lots of things that are sort of variations on this theme that are going to be identified in the years ahead. One of the interesting things that came from this was I was talking with a processor architect, and I used the word bug to describe it, and this person actually got kind of annoyed with me, and I sort of realized, well, why would this person get annoyed when I called it a bug? Because the reason was that everything's working properly. The branch predictors are working properly. Speculative execution is unwinding the state correctly. The reads are fetching things that at least the victim process is allowed to read, although we have lots of intra-process security boundaries that the processor isn't aware about. We've known about covert channels and so forth. And everything is completely compliant with the specifications. And so the idea that you're being criticized for doing something where you comply with the specifications struck this person as kind of unfair. But I actually would argue that if it's not a bug, it's a symptom. And it's a symptom, at first, of something wrong with those specifications. The contract between hardware and software is fundamentally broken right now. And we're going to be learning more over the next months and years about how badly broken that contract is. But the sort of root of it, the root problem is that the guarantees that the hardware provides are fundamentally insufficient for security. You cannot build the systems that we're building today relying only on those assumptions. Which means that, and really the way those assumptions are written or those guarantees are written right now, there's no guarantee that really anything is kept secret, even from other processes, much less intra-process security domains, which are critical for a lot of the different applications that are getting built right now. So if you're a software developer, you either shut down your business and you go home and you decide that you're not going to do anything, or you just make a bunch of educated guesses and you kind of hope that they're right, and maybe you do some experiments on the current hardware to test those. But you have absolutely no confidence that A, you're even truly right in all of the pathological cases an adversary might introduce, and even worse, the next hardware may come up with the great new memory compression, whatchamacallit thing, which creates a whole bunch of new side channels and makes the software that you wrote now catastrophically insecure when it's actually being used by your users. So as research topics go, one of the most important in security right now is the question of what kinds of guarantees should architectures actually provide to the software. And the minimum requirement is that you have something that is sufficient for idealized, perfect software to be sort of secure in some kind of a vaguely defensible sense. That's not really what we need, though. We actually need something more than that. We need something where we sort of minimize the likelihood that we're going to have a problem. And that means actually putting into the equation realistic assumptions about how all of the engineering of the hardware and the software get done. And I'm going to sort of beat on the speculation barrier instructions for about 30 seconds here. I mean, the response to the example I gave before with variant 1 from processor vendors so far is largely put LFENCE or CSDB instructions into your code at the places where something might go wrong. And you're supposed to, as a high-level language programmer working in some language that will compile down maybe through a JIT and so forth into some low-level instruction, put these in somehow. And knowing where to put them is kind of impossible, but if you put them everywhere, you completely destroy security. And even messier, you've got these intra-process scenarios where you may have a language where you'd like to have some kind of safety where you can trust that when I call my decrypt function or my compressed image function that it won't steal all of the data out of my process memory space, but I can't really know that if I don't have LFENCEs everywhere that I need in this other library that perhaps even somebody else compiled. So a huge mess right now, and we need to figure out a solution to that mess if we'd like to be able to build really nice, beautiful things on top of these foundations. And then you can put the challenge on top of that of dealing with performance, power, legacy compatibility, diarrhea, and so forth. So the even bigger symptom here is that we've let complexity just go absolutely nuts in our system. So the history of scaling, it used to be that security sort of economically was this big and the performance gains were economically this important. So everything you could do to help performance was the right thing to do economically for the bulk of users. We're no longer there. Security is a more than $1 trillion a year problem, and the performance gains for many applications are kind of irrelevant because the computers are fast enough, especially for these older applications. So the balance has shifted where performance matters less than security now, and people are even saying this outside of security conferences. It's great. But our mindsets have a big latency. I mean, if you look at computer architecture papers, they don't talk about security. You look at security papers, and they spend huge amounts of time agonizing over the 2% performance hit that they would induce. So we are sort of, our mindsets are wrong. The leadership was built their careers in the old world. Companies built their success in the old world. We have a lot of changing to make. But we need, I think, to build different designs for performance and security. I think we can put them on the same die if we want to. So you can have safer but slower places to run your code, and perhaps faster but more dangerous ones. But we need to figure this out. And this is an enormous research problem that I hope some of you will embrace. All right, I am out of time, so I can take questions for just a couple of minutes here. Peter.
All right, we have some time. Peter Neumann. 2 minutes for questions. As you're doing, please state your name and affiliation. Please.
Peter Neumann, SRI. I have an old world story for you. In 1980, at the very first conference, Hilda Faust, who was the director of research for NSA and a remarkably wonderful person who contributed greatly to the community, was asked about covert channels. She said, and she had, of course, worried about them a great deal inside of the agency, I think that covert channels are she would have used the term low-hanging fruit. I'm sorry, she would have used them, sorry, I botched that. She commented that there's so much other low-hanging fruit that it is almost worthless to worry about covert channels. That was 40 years ago. My question to you is the clean slate architecture question. If you were starting all over today and building processors, what would you do?
Well, I think you shouldn't even start with, say, building processors, but building processors and the kernel around them. And I think that the question is, what should the TCB look like? The minimum set of things, the set of things that your security depends on. And I think we need environments where we can bootstrap really high assurance security, or at least low probability of failure environments for low performance use cases like reading email, approving wire transfers, holding your cryptocurrencies, whatever the things you've got that are, there's a whole bunch of these tasks that you used to be able to do on an offline PC where a machine from 10 years ago is fast enough. And we have a pretty good sense of what the building blocks we need for these kinds of architectures might look like. We have ideas of what encrypted memory might look like. We have ideas of what processors with defined timing, or you can make rules about what is allowed to affect timing, what isn't. Your context switches look very different. If you care about security, it's not how little information can I touch, but how can I zeroize huge chunks of my circuitry. So there's a bunch of properties that certainly we don't have in our current processors that could be put into these. The good news we also have is that transistors are super, super cheap right now, and they're going to even continue to get cheaper. So the idea of putting a small enough processor that our brains can kind of comprehend them onto the die with these sort of monstrous many billion transistor processors isn't a cost issue. It's really just a ideas and effort and one-time investment kind of thing. So I think it is a problem where we can do a much better job. Now, we may screw that up and then find that we need to do yet another more secure environment, and maybe some series of these things that get built over the years, but we've got to start somewhere. And we're not going to get from where we are to somewhere better by trying harder, because complexity is introducing problems faster than we're fixing them. So, and we're also just so overwhelmed with complexity, we're never going to have tools that can really reason about that, and our brains can't either. So we've got to sort of step back, build something simpler, try to understand what its properties are, try to get it used for useful things, and then let the world kind of evolve from there. It's my hope about something that might work.
All right, let's thank our speaker one more time.
Thank you very much.